Hey guys, this video is my submission for the MAT 104 End-Sem evaluation. The question is in the description below. The given ODE represents a mass spring system and we are required to calculate the solution of this ODE. Before we proceed with the problem, I'd like to explain what a delta function is. Delta of t minus a equals infinity if t equals a and 0 at all other places. So graphically it would look like this. 0 at all other places and a sudden spike at t equals a. If we were to integrate this delta function between the limits 0 and infinity, we would get a. Suppose we have integral taken between the limits 0 and infinity, f of t delta of t minus a dt, we would get f of a. So the Laplace transform of a delta function t minus a equals, by the definition of Laplace transformations, we have integral 0 to infinity e power minus st times f of t, which here is delta of t minus a into dt, which equals f of a, which is e power minus as. This is one result which we will be using further down the problem. The question asks us the significance of the delta function in this ODE. What's very unique about the delta function is that large changes can be captured in a small amount of time. That is, if you see until a, the function has remained 0, but suddenly with a very small change in t, we see the function going to infinity. And the delta function is the only function which can capture changes like that. Which is why it plays a very major role in capturing real-time phenomenon like our mass spring system in this question. This is the equilibrium position. If we were to displace it suddenly, our system would start oscillating. And these oscillations would be sinusoidal, which follows from the homogeneous part of our ODE. The auxiliary equation being m equals plus or minus 4i. This would result in a solution like this: y equals c1 cos t plus c2 cos 4t, c2 sin 4t. So yeah, our solution would be sinusoidal. And our delta function tells us when exactly it would start. So this is our delta function, which means before t equals 3 pi, our function is going to be 0. And at 3 pi, it's going to have maximum displacement, which is infinity. And this can be mapped into the graph of the solution, which is it remains 0 until it reaches 3 pi, and then it would start oscillating, which would roughly be a sinusoidal wave. Followed from our conclusion over here. This is a rough estimate of how the graph would look like. We will solve this question and take an actual look at the function. The question is y double dash plus 16y equals 4 delta of t minus 3 pi. Given initial conditions are y of 0 equals 0 and y dash of 0 equals 0. So let's get started. Let's take Laplace transformation on both sides, which gives us Laplace of y double dash plus Laplace of 16y equals 4 times Laplace of the delta function t minus 3 pi. Let's start with this term. Laplace of y double dash equals s squared Laplace of y minus s of s times y of 0 minus y dash of 0. Y of 0 equals to 0, y dash of 0 equals to 0. So we are left with Laplace of y double prime equals s squared Laplace of y. Now let's do this term. Laplace of delta t minus 3 pi equals e power minus 3 pi s, because we've derived the result where Laplace of delta of t minus a equals e power minus as. A here is 3 pi. So we substitute both of our results in this equation. We get s squared Laplace of y plus 16 times Laplace of y equals e power minus 3 pi s, which implies Laplace of y equals e power minus 3 pi s over s squared plus 16. We've taken Laplace of y common and we brought s squared plus 16 to the denominator. I forgot to put times 4 over here because we have this. So that's 4. Yeah, so the Laplace of y equals 4 times e power minus 3 pi s by s squared plus 16. To find y, we take inverse Laplace on both sides and we get y equals inverse Laplace of e power minus 3 pi s times 4 by s squared plus 16. Considering the second shifting theorem, we have Laplace inverse of e power minus as times f of s equals f of t minus a times u of t minus a. This is what we previously found, and this is the second shifting theorem in inverse form. Comparing both of them, we have f of s equals 4 by s squared plus 16, implies Laplace of f of t equals 4 by s squared plus 16, implies f of t equals Laplace inverse of 4 by s squared plus 16. We already know that Laplace transform of a by s squared plus a squared equals sine at. So this can be written as Laplace of sine of 4t, which implies f of t equals sine of 4t. From all of this, we can write that y equals Laplace inverse of e power minus 3 pi s times 4 by s squared plus 16, which equals f of t minus a, which is sine of 4 into t minus a times u of t minus a, implies y equals sine of 4 of t minus a times u of t minus a. And we have a equals 3 pi, implies y equals sine of 4 times t minus 3 pi into u of t minus 3 pi. This is our solution for the given ODE, and if we plot it using a graphing calculator, we get this kind of a sinusoidal wave. This is almost exactly like the estimate of the graph that I previously drew. Thank you. Have a great day.